All right, we are in week 6 of this class, by the way. It is flying quickly. So, all right, so this week is titled Dealing with Deadlocks. We're going to look at, for your asynchronous lecture for today, for this week, you're going to watch the Dealing with Deadlocks recording. That's the oops, that guy in there, pre-recorded lecture for this week. And the Dealing with Deadlocks PPT that goes along with it if you're looking for it. And then what I'm going to do today is the classic IPC algorithm demos to pick up where we left off. So last week or the week before, I stopped the IPC lecture halfway in between. And I'm just going to pick up where I left off. Okay, good. All right, question, comments, concerns before we get started. If you have submitted assignments 1 and 2, they've been graded. We'll be working on assignment number 3 if you haven't started that one yet. So thank you for passing that attendance thing around. All right, so it's hard to pick up in the middle of a lecture where I stopped, so I'm gonna sort of try, overlap it a little bit. Talking about semaphores and mutexes, and we were talking about producer, consumer, reader, writer, dining philosopher, sleeping barber, some interesting IPC algorithms, as I call them. So I want to start in with this one called library. And the library example is all of these examples I'm going to show you right now are in the course materials. It's the last one on the list called the library Java examples. So I've got both C and I've got Java for you. So depending upon whether or not you've chosen to do the assignments in Java or C, you have your choice. I prefer Java, obviously, because it's simpler and more automated. However, you might want to use C because that's what you'll be tested on for the systems exam. So you do want to be familiar with the C as well as the Java. But for the most part, for accomplishing the assignments, you might enjoy using Java, I believe. So, all right. So in this particular example, we have a library. And in the library, we have books. And we also have readers that come to the library to check out books. We have an unlimited, or we could have an unlimited amount of readers. In this particular scenario, we're going to have 6 readers, I believe. And then we have 3 books. So they can't all get a book at the same time. Excuse me. I'll pass it yeah, as well. Thank you. So the scenario mimics counting semaphores, because we don't want to use a mutex for this, obviously. We want this to happen interactively. We want concurrent threads. And so there's a nifty little library and system that we can use in Java that's going to automate it for you. I also showed you the same example with counting semaphores with C. If you remember, it was a couple weeks ago. If you go back through your notes, you'll see it. But for the most part, we'll pick it up here. So we have this concept of a book. And so what I've opened up here then is the, in fact, let me compile this actually so we can make sure we know what this program is doing here. There we go. I put the main in a program called main.java. So we have Java main. All right, oops. Of course, I Java twice. Oh, there we go. So you can see as the example starts out, it's in an endless loop until everybody has read a book. So the 6 threads are created, the 3 book threads are created, and they're matched up. The reader acquires a book and then releases it, and then another reader comes in and acquires and releases. So it's interesting, and if you run this a couple of times, you'll see the output looks significantly different each time, or not, I wouldn't say significantly, but if I run it again, I just look at the top here. And let's see, we've got Rama, okay, let's see. So I'm familiar with what's on the top here. Let's run it again. Similar. It's because there's a race condition in the beginning. The race condition could be mitigated, could be helped, but for the most part, the output is not guaranteed to be the same each time. And the order that the books are returned are going to be different as well. Because what we're looking at is concurrently running threads that are all competing for the same resources, and we're using semaphores to control the access to those resources. So the scenario comes in handy for a lot of semaphore implementations, which is why I decided to show it to you. So the book, regular old class Java class, nothing too fancy about this one. We have a constructor in here, creates an instance of a book with a book name. We've got a read, so a read method that's going to implement a little slight sleep in there too, but we've got a little system out. Obviously, the whole scenario is mimicked through system IO. So we've got a little, a little message that gets printed to the screen, and then we're going to sleep a little bit. And that's about it. We got a get book. It could be completed with setters and getters and all the other stuff. But for the most part, it's kind of a stripped out example, but just showing you the basics of the semaphores. So there's our book. And then we have a reader. And like the last time I showed you, when I started this lecture, actually a couple weeks ago, we had two forms of implementing threads for Java. So we can implement the interface runnable. We also have to, both mechanisms, we have to implement the run method. So this one's implementing runnable and implementing the interface method run. We can also just extend thread. So we could do it with inheritance as well. That option is nice because sometimes you're already extending another class, and in Java, you can only extend one class at a time. So you have the option of doing either the interface or the extension, so the inheritance. So for the run method, and so the books, the reader itself is running as a thread. We know this because we're implementing the runnable interface for it. In the run method, we're going to do a little try and catch, which is pretty standard actually, where we're going to create instances, a book instance. So book is equal to, and we're going to cast it to a book. And we're going to do the library issue book. So I haven't shown you the library yet, but when we look at the library, we have books that are issued. So this is a really good design pattern actually to separate out your threads and separate out your concepts so that it makes logical sense. It kind of mimics a real life scenario. So, all right, so the reader, and a little constructor here. The reader needs to know about the library. Now we could have more than one library. And if we do, and when I show you the dining philosophers, you'll see that there's a possibility of having more than one resource that they're competing for. Here we don't have to worry about it. If they don't have any books, they go to sleep. And then the reader comes back and tries to get another book. So we have the run interface. We're going to implement create an instance of the book, and then we're going to run the book read, because that's what the reader does. He reads a book. So book.read, and that's in the book functionality. And then the library return book. So after the book is read, then we're going to go back to the library, which I'll show you in a few minutes, and then we're going to return the book. And then catch any exceptions that might exist. So if we take a look, let's take a look at the library, because that one seems to be coming up here. All right, so in the library at the top of it, I put the source of this actual example. This is a modified version of what is at this URL. If you go to that source, you'll find like 2 or 3 pages of reading on counting semaphores, actually. It's not a bad resource if you're still kind of iffy on when do I want to use a counting semaphore, or when do I want to use a semaphore. And really, a counting semaphore is just a semaphore that's not a binary semaphore. So it's one that goes higher than a on or an off. So when we have quantities like 3 books, we want to do a counting. So we can count up 3 instances of these books, keep track of them as they're allocated. And really what we're doing is just allocating resources, so which mimics what the operating system is doing. So in our library class, we are implementing from the concurrent semaphore library. So that is the library import that you'll be using for that. And Java doesn't actually have a mutex. They just have a semaphore. So you just make a semaphore into a mutex if you want to have that one at a time serial execution. So just to refresh your memories here, the mutex one at a time, semaphores multiple at a time can run. And when we're looking at concurrency, when we're looking at counting semaphores, because we don't want there to be serial execution. And by serial execution, I mean, we don't want things to happen like with multiple threads that could possibly happen with just one thread. Like there's no need to create multiple threads if you're going to have one action after another, and it's always in the same pattern, and there's nothing running simultaneously. And here we want that simultaneous because we have 3 books that we want to loan out. So we've got a semaphore available books, and we're using the semaphore to keep track of how many we have. So we started out, I believe, with 3. In our book array here, we've got 1, 2, 3. Yes, my memory serves me correct. And we have a maximum permit. The maximum permit, we'll set a little constant variable there to 3. So if you had 12 books, change it to 12, the scenario would still work. So we've got 3 books, and then we have a flag here, a Boolean flag for being read. So we want to know, is something being read, which means it's busy and we can't acquire it. So there's a check before we acquire it to see if it's free or available, rather than like blindly as a race condition going through and just grabbing whatever's available. So it makes it fair, I should say. So the book is issued here to the reader. Little method here, object issue book. And it's just kind of a generic object. It doesn't really, it's going to throw an exception though, an interrupt exception. But here's the big one here. So the available book, and this is the semaphore available book. We just have these 2 methods that we're going to run on it. One is the .acquire to acquire it. The other one is the .release that we're going to see further down. So we acquire it, and then we are going to return the get next available book, which is going to be another method that we're going to run to get the next available book. So it makes it so it's available for the next reader that comes in. And like in the last lecture I showed you, we're using that keyword synchronized here. So with the keyword synchronized, you don't actually have to do very much. The Java monitor system will see that only 1 thread at a time can access this method. And this method is the get next available book. You don't want to put synchronize on everything. You only want to put it on something that matters, such as a counter, a flag, a method like in this case, to find out if something is available. And it really creates what I was calling serial. It really creates a serial process. So if multiple of these readers are going to go and use this method at the same time, they're synchronized. And they're synchronized in a serial fashion. So there's 1 at a time access to it, which is what that synchronized keyword is going to do. So we can put that synchronized on a method. We could put it on a block of code. We could also put it on a class object itself. And lots of flexibility with this. Here we're just putting it on a method. And because we're putting it on a method, we don't really need to do anything else to the method to synchronize it. We're not going to ever have, and what we're trying to prevent are things like deadlocks, race condition we can't really prevent, but we can mitigate by the logic of the program. And here we create the books first, and then we create the readers second, and then the instance of the library third. We'll see that in the main in a few minutes. So that it prevents this unusual race condition that might happen with readers trying to get books before they're not available yet. So, and it's just like the producer consumer that I had shown you with the copy file scenario. If we're copying a file, we're going to want to say the producer is going to run first and then the consumer is going to run second. Otherwise, why should the consumer run first when there's nothing to consume, nothing to read out of the buffer? So we're going to mitigate that race condition with with our main activity, just because we want to control the order to start with. But after that, if we had a race condition that's synchronized on this method, would prevent that from happening. It's also going to prevent a deadlock. And we're going to see in the next example with the dining philosophers, sometimes we want to avoid the hold and wait scenario as well. So here we don't have a hold and wait because as soon as the reader is done reading a book, they're going to return it. And then we're going to update a data structure to say how many books we have available left. And so if we have any available books left in the system, then the reader can go ahead and start checking out a book. Otherwise, if there's no books available, then they just go to sleep. So what's going to happen with this? Okay, so the book is null. I'm going to do a little loop here. Is it being read? We're going to say it's true. We're going to set a flag to see if a reader has acquired that book. If so, we're going to set the flag, and then we'll print something to the screen to let us know what happened. The book.get book name, and it's going to be has been issued. So we're issuing the book, and then obviously we have to return the book. So we have another method here. Now the return is not synchronized. Again, going back to what I was kind of saying in the beginning here, or I said a couple weeks ago actually, as well. You don't want to use the synchronize on everything. Only use it when you absolutely, it's necessary to use it. And I would wait until you're done with the implementation and then start synchronizing methods. Only because it will slow down the system, because it will stop multiple threads from running in that method at the same time. So if you want a higher performance, then don't put it on return book. You don't need it. So on the return book method, mark book as available book. We're going to take the available book and we're going to run a release. So the available book is the semaphore that was defined up here at the top. Semaphore available book. And it has 3 associated with it, which means we have 3 semaphores that can be assigned, and each semaphore correlates to a particular book. Now, which one does it correlate to? That's a good question. It's not actually assigned. However, you could, because of random run of the draw, you could assume that it's book 1, 2, 3. But the order doesn't really matter. And if you run the program a couple of times, you'll see the books are issued out of order. They're just issued at a random, whatever happens to be available at the time is issued. So these readers are not very selective, I guess is what I'm saying. You can make them more selective. They could wait for a particular book if they wanted to. And if that were the case, we'd have to change the semaphore design here. Instead of having 3, we could only have 1 of each book, or maybe we have multiple copies of each book. We could also implement that with a semaphore. So when you have more than 1 item, you need to use that semaphore. Otherwise, you could use a mutex if you only had a single book. So, and which is the difference there. Okay, so we have another synchronized method, and this one is the mark as available book, which means we're going to signal to the system that, hey, this book has been returned and now it's available. So when the next reader comes in, it can look for the available books and essentially be able to select a book to read. So here we have it returned, printing to the screen, setting a Boolean flag on whether or not it has been returned, which is important. And if it's not being read, then change the being read to false instead of true, and then set the flag to true, which means which is going to be the flag to indicate that we have a book that we can loan out. So all of this functionality is part of the library. So the library attaches, and this scenario lends really well to the implementation of, well, a couple of your assignments actually are going to use something, the later assignments, the ones you've had so far haven't required the use of semaphores. However, you're going to run into this, so it's not a bad example to kind of download and look at in the future anyway. Because you might end up needing to look at some of the design pattern here. So we did the reader, we did the book, we did the library. Let's take a look at main. Main you're going to love. Main's great. So why is main so good here? We have an executor service. So this I have not shown you yet. So we're going to make here an instance of this. It's from the same library, concurrent, and it is the executor service, also importing executors. So what in the world is this? Just like the monitor system. So we know we have a monitor system, goes out, checks, look, that's how synchronized works. Goes out, checks to see if there's a deadlock, if there's a condition where we've got like something happening that's stopping the execution. Here we have an executor service that we create using executors.fixed, new fixed thread pool. So in non-programming terms, we are creating a pool of threads, and the pool of threads are going to be representing the readers because we have 6 of them. So this particular case, if we were going to create like a dozen or so of threads to accomplish something in this particular case, if we use the executor service creates the threads for us, joins them together in the same pool, and runs the monitor service on them. So it avoids conflict, avoids deadlock and other issues. This is the one reason why I actually personally like Java. It's because they thought about it ahead of time instead of having to manually do it in C or C++, where you've got to create all those manual threads, then you got to join them together, then you got to assign them a method, or you got to tell them what to do. This is like one line of code that does like maybe 10 lines of code in C. So we've got, and it's easier as well. So this EX service is what the instance of this is called. So we make an instance of this, and we're using thread count here, which we've hard set to 6. So this will create 6 readers. One of the things that you can do with this example is double the readers. Just change the 6 to a 12 or something, and then see. This program should not deadlock. It should not have starvation issues. It should not have anything, actually. It has a slight race condition, but it's solvable. It's something with the way I have well, this is the main here, but I didn't put anything in here to avoid any type of a race. So the three books get processed essentially with the first 3 threads sometimes. So, but it's not really a problem. Okay, so this is main. So we're gonna use the executor service to create a thread pool of 6. So these thread pools, a little bit more information on this one here. It's kind of like if you were implementing the producer and the consumer model, and you had you were going to do it for a CP command, copy command in Unix, and you had a 2 gig file. You'd use a larger thread pool than you would if you had, let's say, a 20 kilobyte file or something. I mean, the size of the file is just really huge. You could use the executor service to create a pool of producers and a pool of consumers in the very same way as we're creating readers here, and benchmark it. So take, let's say, get the size of the file that you're copying and say anything between this size and this size, it's going to get increments of 10 threads or something. And so the file copying would go faster for a larger file versus a single thread or multiple thread, a couple of threads. You could actually benchmark it a little bit, or I don't know, create a scenario where you're taking the size of the file. And so each file copy would run differently depending upon the size of the file. You'd have a thread pool of the producer, thread pool of the consumer, and all running concurrently and all being managed by the executor service. So to avoid any problems, that would be a slick implementation. It's pretty much not using the executor service because this is done in Java. The Unix implementation is actually done in C, but similar concept is actually being done. The size of the file is considered when you're going to copy it. It just takes a second to get the size of the file, and then you can have a much faster copy if you're doing it more efficiently. So anyway, just keep that in mind. The library, instance of that library, and then the readers. And here's where I say I'm really kind of creating a race condition anyway with the readers. So we've got readers equal to new reader for the library, executive service to execute. This is how we're going to execute it. And we're going to execute it on the reader. So we've got that new instance of the readers that are created with the thread count of 6. So we've got 6 threads created. And at the end of main, when main is done, we're going to shut it down. So really just 2 lines of code to actually create this thread pool for you. So feel free to branch out with thread pools with the executor service, actually. It's not a bad implementation. So. Alrighty. Anyway, that was the last example from where I left off on the last lecture with the producer-consumer and the threshold. This is not a producer-consumer model, by the way. Actually, you might think I'll tell you at the end what this is, but think about what model this actually implements or what model this shows. There's a couple of them in there actually that kind of mimic. So, questions on this one before I move on? Nope. Okay. Good. Very good. All right. Let's look at dining philosophers next, and that one I'm going to show you a C as well as a Java one. I showed you the library with a C example already, so we don't necessarily need to do that, but let's take a look at the dining philosopher's problem. All right, so this is also the IPC, classic IPC.ppt file that's also in the course materials for this. I copied it as well into the course materials this week. So you've got an uneven amount of resources. You can read the little thing while I'm talking, the little description. I should make it a little bit bigger for you guys in the back there. Oh, that's big. That's big. You have, and this really does mimic more of an operating system scenario than any of the other algorithms, in my opinion. But you've got, in the classic scenario, you've got 5 philosophers sitting around a table. The old scenario had spaghetti with a fork and a spoon. Now they have chopsticks with rice. Whatever you have this unlimited resource in the middle that you're trying to access. But in order to access it, in order to eat, you've got to pick up 2 other components, 2 other resources. So this is really a resource allocation scenario. So, and the dining philosophers, the problem that we have there is the hold and wait. So what ends up happening, if you don't have enough chopsticks for everybody to eat at the same time, depending upon the order, one of the philosophers or one of the threads that it's requesting a resource is not going to get it. In fact, if everyone picks up a resource and holds on to it, it's possible that nobody is actually able to complete their task. So you need multiple resources to complete this task without doing a resource graph or without doing any of the things which is upcoming in next week's lecture. Without checking for this particular hold and wait, you can actually fix it by programming, which is what I'm going to show you, just with the method that you're doing. So each philosopher has this bowl, they have these chopsticks. Occasionally a philosopher gets hungry, he's going to pick up a left, he's going to pick up a right perhaps. Maybe, hopefully he'll get both. If he doesn't get both, he needs to put one back, which is the classic scenario. So how can you help these philosophers to synchronize their use of the chopsticks? Well, before they pick up the second chopstick, the technique that I'm going to show you is to check to see if the resources are available. So it's a pre-check. So once you have a chopstick, you got to check to see if there's another one available. If there isn't, you got to put that chopstick back. So it basically prevents the deadlock situation with the hold and the wait. So the cycle sort of looks like this. We got to think for a while, pick up a chopstick, eat for a while, put down a chopstick. And this could be opening up a USB drive and getting it ready to copy, perhaps bringing up into a file manager of some sort or view, and then opening up a hard drive and then copying from a USB drive to a hard drive. This could also be using a printer, let's say, with a scanner at the same time, scanning something and then printing it out or something, whereby you're using, let's say, 2 different resources. Whenever you have multiple resources needed for a process to complete a single task is when you're going to get hit with this dining philosopher scenario. And when I say it's a scenario, it mimics the problem, and the problem itself exists in a lot of different forms. So it's not just one problem you're solving with it. You're using it as a tool to solve multiple problems. And it can be used, the scenario can be used to prevent the hold and wait, essentially. So any problems with this algorithm? Lots of problems. Thinking for a while, lifting up, putting one down, waiting and eating, and then unlocking. Because you'll have to use a couple of semaphores with this, in this implementation. But then you also have this scenario here where you've got a lock that's going on. And what what scenario do we have here, actually? We have a lock on A and a lock on B. Let's say A is one chopstick and let's say A is one philosopher and B is another philosopher. And they're both locking something and they both need the other item. So it's the hold and wait, right? But it's also what's referred to as a circular wait. So A is waiting for B, who's waiting for A, who's waiting for B, who's waiting for A, yada, yada, yada. So it's a circular wait as well. And that's what you're going to get. And maybe that's why they called it a dining philosopher, because you always see a round table. So remember, a round table, circular wait, hold and wait, multiple resource allocation. So, all right. So the deadlock can occur whenever multiple parties are competing for the same resource at the same time. So a lot of operating system vendors say, well, just add on more hardware. You know, we're running out of use. Oh, just put on another port. And which is another way. It is an expensive way of solving the problem. In fact, that's what they do with memory. So you run out of memory, I'll just add more memory, and we don't have to compete for the memory. But adding on hardware is not necessarily possible, actually, depending upon the architecture of the computer system you're on. So you can avoid deadlocks. We went through this already, and excuse me. It is also the prevention, avoidance, detection, and recovery. And the conditions for deadlock is also in the asynchronous lecture that you're going to be watching for this week. So you'll get a little refresher on that, if you haven't had it in an undergraduate class, assuming you haven't had it before. So if you have, then I would skim through it. Necessary conditions for deadlock. You need to have that mutual exclusion, which means, one at a time, going into a critical region by definition. But it's also, while I'm using a chopstick, somebody else can't use it at the same time. It's mutually exclusive. And the hold and wait is another condition that causes that deadlock, as well as non-preemption. And non-preemption is when you cut it short, which is what this example that I'm going to show you next is going to do. If you don't have access to another chopstick, then you got to put that chopstick back. So you can't use it. And then that circular wait, which is also a common problem as well, which I just looked at a few minutes ago. So in the hold and wait, a thread or process that needs a resource is currently taken hold of other resources already has and waits for the resource. Yeah, you're holding on to something, you're waiting to see if the other one becomes available. That could turn into a starvation scenario, but it doesn't always. So lots of students get confused between the deadlock and the starvation in the scenario. Apparently, and with dining philosophers, we could jokingly have a starvation. You have, basically, you have philosophers who are not allowed to eat because they can't get a chopstick. Could that lead to a deadlock? Sometimes it will, if there's a hold and wait. But in order to get that deadlock, you need one of these conditions: prevention. You need a mutual exclusion in order for that to happen. You got to have that hold and wait going on. Not that it's a good thing; it's not a good thing. You want to prevent this deadlock. But if you do have that hold and wait, be very suspicious of deadlocks and be very suspicious if you're not preempting. So we're going to preempt in the next example. All right. So no preemption. Basically, we'll never get a resource that it's holding on. So basically take it away. So, all right. Banker's algorithm. Yeah, stop here. So in the lecture that you're going to have for your asynchronous part of this week, I go through all this. I cover this part. So I'm not going to do that one. I'll come back for the Banker's algorithm in a few minutes. But all right, we want Dunning philosophers. So in the Dunning philosophers example, I put it all together into one file. And I did this for your convenience because it's easier to download it and to look at it. So just think it should be separated out into each, basically each class in its own file kind of thing, it's very standard Java. So this one, just take that one with a grain of salt in terms of the way I'm delivering it to you. So let's run it so we can sort of see. And unfortunately, I made a really long file name. And let's see, wait a minute. Let's go back to desktop. Oh, actually here, it's just, I don't know where I was. There we go. All right, let's see. We're looking at dining, philosophers problem dot Java. Of course, I am not spelling it right. Let me try that one more time. Dining. I should basically shorten these things, shorten the names. Dining philosophers problem Java. There we go. All right, so let me run it. Oh my God. Next time I make a shorter file name. There we go. There we go. So we got philosopher 1, 5, 3, 2, 4. They're not in order. We also have a race condition going on, but in this particular case, 1 grabs the left chopstick, 5 grabs the left chopstick. They're all grabbing left chopsticks. So the order starts with them all grabbing the same side on the left. So if we had it intermixed with some grabbing the right, some grabbing the left, it would be more complicated in order to orchestrate it, how this works. And the way that this is going to happen is that everything is going to complete before the program ends. So we make the instances, I believe we also make 6 philosophers, just like they had 6 readers, but I'll check on that in a few minutes. When we're all done, everyone eats and then we exit the program. So if we run it a couple more times, we have 3, 1, 4. So we have 1, 5, 2. So you see it's different. So when you're implementing this scenario, or you're implementing using semaphores in this fashion, you want to run it a couple of times to see that the output is different each time, because that's the nature of the multiple threads running simultaneously. So, all right, so let's take a look at this code. Did not use the executor service in this one. This one's done manually. And so we've got the thread local random now. That's a different one I haven't shown you yet. So we have concurrent semaphore, then we have concurrent thread local random. So we have the main class here, where we've got dining philosophers problem. And we have 5 philosophers, okay? So we have 5 philosophers created. And the philosophers are going to be equal to new philosopher. We're going to create an array of the philosopher object. So further down, there's this class object called philosopher. So as before, unfortunately, I put it all into one file because there's too many small little pieces, and zipping it up was, I guess, probably better. But anyway, we're also going to have an array of chopsticks, and we have a chopstick object that we're going to use as well. So static class chopstick, which happens to be the next one in the line here. So this one is actually using a mutex. So we got the semaphore mutex, which is equal to new semaphore 1. You don't have to call it mutex, but because we're using a single valued semaphore, we're going to call it a mutex because that's what we're really doing, because Java doesn't actually have a mutex. Then we have a grab method. And same as before, we have a dot acquire and we have a dot release. So for the mutex, we're going to acquire it. And then for the release, we're going to dot release it. Oh, wow. It sounds like it's going to start raining now. Watching the weather. But here's the $15 million piece of code to keep in mind. It's the is free. So is free is very important. We're going to check to see mutex.available permits larger than 0. Which means if we have a counter keeping track of how many chopsticks we have, and it's larger than 0, then we know there's a free one. And so then we can acquire that free one. So that's the end of the chopstick class. And then now we have the philosopher class. So this one is extending thread instead of implementing runnable. And the chopsticks aren't threads. The chopsticks are just regular old objects. So which is interesting. Not everything needs to be a thread. So, but the philosopher is a thread in this particular case. So public integer number, which we're going to keep track of how many philosophers we have or how many numbers. So we have a chopstick that represents the left side. We have a chopstick that represents the right side because you need two chopsticks to pick it up. We have a constructor for the philosopher, which is going to take in a number and then a chopstick left, chopstick right. And we're going to assign the left to the left, the right to the right. Now, for all intents and purposes, all of these chopsticks are the same. A chopstick is a chopstick. Whether it's a left chopstick or a right chopstick, we need to keep track of that because if we have a pool of open chopsticks, they might pick the same chopstick twice, which happens actually in resource allocation when you're trying to copy, let's say, from a USB drive to a hard drive. You may end up picking like the wrong, picking the same resource twice, even though you only need one of each, I think. So even though they're the same resource, you want two of them. So anyway, that's why we're keeping track of the left and the right. Otherwise, if you just needed two, we don't really have to keep track of which one is which one. So we're going to implement the run method, and then we're going to grab the chopstick. So left chopstick dot grab method, and our grab is up here. Here's our grab. Here's our grab, where we're going to do the mutex dot acquire. And we're going to put a little system out that says philosopher and then the number of the philosopher. Now, this is kind of hokey. I did a +1 because we're starting with 0. And we don't want to, philosopher name 0. So it's 1 through 5. So it's going to grab a chopstick. The other one's going to grab a chopstick. So we've got the grabbing chopstick. One grabs a chopstick. So they're only showing the left chopstick, but they're going to get the right, then they're going to complete. So let's see. Eating, we've got an eat method where the philosopher is going to eat. We have a left chopstick dot release. We have a right chopstick dot release. And then we have an eat method. And so this eat method is where everything is going to happen. Well, basically it's like hello world. It's going to print something to the screen. I'm eating, and that's about it. They're not really eating. So the sleep time. Here's so we're doing the sleep time. So we have the thread local random dot current dot next int, and then we're going to go between 0 and 1,000. We're going to randomly sleep the philosopher. So if you're looking for a nice random method, this is a good choice. Because this is the one that's coming from thread local random from concurrent. So it'll keep track of, it'll do a nice implementation of a sleep for your all intents and purposes. So thread.sleep with the sleep time that we're getting from the random. So, and then here's our main program. So we have a chopstick, just like the library layout. If you copy and paste and put it in different files, just like the same scenario, we have a philosopher, we have a chopstick, we have a main, and then we have, well, that's about it, actually. So it's got one less. We don't have a library here. All right, so main. So main is going to loop through the chopsticks. And so chopsticks is equal to new chopstick. What is that? Get rid of that. So we have for I is equal to 0, I is less than the philosopher, I plus plus. Philosopher I is equal to new philosopher with chopstick I plus 1. So we're basically assigning the chopsticks per the, not really random, just per the order of the chopsticks. And then philosopher.I.start, because remember this .start starts the thread and the philosopher is a thread. So we're doing a thread on that one. And then while true, this is where the logic is actually cool. Thread.sleep 1000, I'm gonna sleep a little bit. And then set a flag for deadlock, because what we want to do is detect a deadlock. So for each loop, iterate over the chopsticks. So for chopstick CS, short for chopstick. So there's a shorthand Java method. If you haven't figured out the looping, Java's got some really cool looping, actually, that's different from, it's very Python-ish, actually. You can do a counter-controlled or a data structure-controlled loop. And that's what we're doing here. Check to see if the chopstick is free. So cs.isFree, which it returns a Boolean true or false, which is from the isFree method up here. Somewhere up here we have an isFree. So break. If it's false, if deadlock is equal to false, we're going to break out of that loop. We don't need to wait any longer. So instead, the deadlock occurs if the sleep time is 1000 milliseconds, means each philosopher is eating. So if the deadlock, if there is a deadlock, then we're going to sleep and say everybody's eaten because it's going to deadlock, meaning that all of the resources are allocated and there's no more chopsticks available, which means they should be eating at that point. And then we're going to exit out of the program. So the big trick here is checking for the deadlock. So in most cases, you don't necessarily have to write deadlock as a condition or as a Boolean and actually manually check for it. The executor service would help in this scenario. In fact, if I created those philosophers using the executor service, I wouldn't have to check for the deadlock because that's what the executor service is doing for us. So it's making those threads cooperate with each other. So I would have a pool of philosophers that will behave themselves. So anyway, so this one could be improved. I don't have a URL for this one. This is my own example, but you can certainly convert that one. I used to have an assignment in the old days that converted it, that had you convert it, but I decided to give you signals instead. So, which actually, intermission here, intermission break. If you've completed assignment 1 and 2, I've tried to stay up with the grading. I should have it. You should be working on assignment number 3, which is the programming signals. That one is due on March 8th. So that's the one you want to be doing. It's like February is going to be over with at the end of this week. So yeah, we're already into March, which is incredible. February 22nd was when the process synchronization was due. I think that was this one here, actually, the island and the parking lot. If you look at that, so I remember at the beginning I said, or when I was going over the library example, I said, what scenario is this? It's actually a combination of producer consumer and sleeping barber altogether. So sleeping barber does a queuing solution. I'm going to be going over that as well. Still have a half hour left here to get through this. So what you're looking at with the sleeping barber then is keeping a queue of people or resources that need something else and then matching them up per the queue. So it's not a real-time scenario. That might not be a real-time, like, immediately, as soon as a car indicates that it's wanting to leave the island and go to the mainland, it doesn't have to happen immediately. It can be queued up and then you can synchronize it, which is very similar to the banker's algorithm, actually. So this particular assignment has a lot of different components in it. So that's why you're doing it, basically, is to implement these algorithms. And remember, for the capstone, you need to use C, by the way. For this class, you can use Java for everything. For the capstone, they used to have it just C, but you might want to check before when you start prepping for it. They give you, when you sign up for the capstone, if you guys are doing the capstone, not the capstone, excuse me, the exam. Yeah, the exam, not the paper you're writing, but if you don't do the paper and you take a test, the systems part, you'll be assigned an advisor, probably Leanne, actually. It's not here anymore. But you have you'll get an advisor that will help you. And then basically they go through the sample problems from the previous years. And long story short, it used to be, though, everything had to be written in C. So you might want to check to see if they've broadened that out a little bit, because it was kind of in my opinion, kind of a stupid requirement. Because C and Java are so similar. Anyway, and you can create a thread in Java as well as C. So anyway, not to keep knocking C, but once you do Java, you don't want to go back to that. I don't want to go back to that anyway. All right, so I did have a C. Let me show you real quick then the the C implementation of the dining philosophers, as soon as I get that thing out of the way. Here it is. So we're going to use pthread, we're going to use semaphore, and this is truly C. And we're going to keep track of the states, thinking, hungry, eating. And then we're also going to keep track of the left versus the right. And we're going to keep track of the number of them. And now we got the states in here, along with their IDs. We're going to use a mutex for this one. Even though we've got the semaphore library up there, excuse me, we're doing a semaphore, but we're creating it sort of like, we're calling it mutex, but we're using a semaphore like a binary semaphore in this particular case. So in the main method here, we're going to test the state. So we test it before we attempt to assign it, which is the key. This one uses a slightly different implementation technique. It does a test before, where the other example that was in Java does a test after you already have a chopstick. Then you're going to pick up another one, you're going to test it. This one tests to see if you have both of them available right now, instead of just picking up one and waiting. So, which could be a better implementation. I'm also going to implement a sleep in there. So in this one here, dine fill, a little easier. This is a GCC, dine fill, oops, .c. I'm going to get some warning messages because it's an old C library, basically. And I didn't give it a name, so it's a.out. But very similar. We've got 1, 2, 3, 4. This is going to go on. I believe this one might be an endless loop, by the way. So this is just going to go on forever. So until it deadlocks. But the idea here is we're programming it to avoid the deadlock. So in this particular case, if I ran this for like several hours, it should still be running. If it stops running, it means I got a deadlock. So it's running pretty good right now. So, but you can see that the threads are working independently and they're not in the same order, and they're randomly just happening in whatever order that the forks, and this was using a fork actually, 2 forks instead of a chopstick, same scenario. All right, I'm going to stop this because it's going to run forever. There we go. All right, I'm going to try and get through these examples today, so let me pick it up a little bit. So we've got a take fork, a put fork, and you're using 2 forks. So I guess you could modify this to use a fork and a spoon if you're Italian. I don't know. In the main method, we're using the old-fashioned thread underscore create to create the thread, and then we're going to use a thread join to join them together. So that's what I was talking about. The executor pool is a little bit more efficient because I don't have to create them and then join them together and then use them. I can just one spot, just create them in a pool. So, all right. So dining philosophers, give me the banker's algorithm. So unless we have questions on the dining philosophers, I'm trying to get through all these examples today. So let's see. So the idea with the banker's algorithm is that we have a limited number of resources. And before we allocate the resources, we have to make sure that the state is safe. Because we could have a situation where if we allocate it out in a certain order, other people won't be able to receive funds, which is basically how the banking system works in this country, actually. They don't have enough money to give out to everybody. They only have a certain amount of money. And so they keep loaning that money out to multiple borrowers. And it's the order that they're lending it out that makes it possible. So in order to lend out anything, you have to run through a scenario to make sure that the state is safe, whereby if I lend this out, then I'm going to also be able to lend out for that person, that person, and that person. So you can have the most number of lenders or borrowers, most number of borrowers for each resource allocation. So maximize the number of borrowers, basically, because the banks want to make money and they make money off of your interest. So when you return the money, you pay it with interest. goes back into the pool. Well, they're counting on that. So what happened actually, which is a real life scenario in this country not too long ago, is that the banking system collapsed because borrowers couldn't pay back their loans because they had some bad interest rates or whatever was going on. So borrowers weren't paying their mortgage payments. And then the lenders were, banking algorithm failed. So everything became unsafe and unstable. And then the federal government came through and gave them money, which bailed them out. So anyway, real life scenario. So what we're looking at in this algorithm is the safe state. And so in this particular case, a new process must declare its maximum resource requirement ahead of time. And then when the request is made, you have to check through to make sure that all of the other requests can also be satisfied. So you're going to maximize the number of requests. So let's put it into operating systems now, outside of the banking system. The system has 12 tape drives, let's say. And we have 3 processes that are using these tape drives. And you have to have a maximum need specified. Like, how long do you need this for? And this might be a maximum, it might be time. Might need it for 10 minutes or something, or we might need 10 tape drives, or whatever the scenario is. We need to know how much this borrower needs. And then we also need to know at any one moment of time, how many do we have allocated? How many do we have left? And then in a time schedule, that allocation changes when borrowers are putting back, I'm done with this tape drive, I'm going to put it back into the system, somebody else can use the tape drive now. So it's kind of a give or take. In this particular scenario, if you ever see like questions like this, the question is going to be, is the system in a safe state? And then what if we allocated another tape drive to P2? Would it also be in a safe state? Well, it is in a safe state. This particular scenario is 3 tape drives are available in P1, and P1, P0, and P2 would be the order of the allocation. If we allocated it in this order, it would not be safe, because what's the criteria for safe and unsafe is going to be, can we allocate it to all 3 processes? And so it's the orchestration of which thread is going to get it first, second, and third that's going to create the safe or the unsafe states. So here, if we gave P2 another one, it's not going to be safe because it's over allocation. So what if we allocate another tape drive to P2? Nope, not safe. Only P1 can be allocated, allocate all of its required resources. P2 would still require 6 drives here. So in the textbook, actually, if you have the textbook for this class, in the threads and process, actually there's an entire chapter on IPC, and they show you a couple of different mathematical approaches to, figuring out if the condition is safe or not safe. I've never seen this asked on a capstone, but it is part of systems. So they will show you scenarios. You will see, if you take a look at, I gave you guys the resource, right? At one point. Let me give the resource to you. If you just type in CSUED capstone sample exams. There we go. These are all of the systems, is what we're looking at here. Systems exam. So in fall 2025, on the systems parts, see, you don't have to answer all the questions. I think you get a choice between which one you're going to answer. This is memory management. Some they do IPC in here. Least recently is. We're going to get to that shortly. Bankers, here we go. This is a good one. Bankers algorithm. So this material is very relevant to what it is you're going to have to take the end of, usually towards the end of your program, like the last semester, second to last. So we have the allocation, we have the max, we have the available. And if you look in the textbook, I'm going to leave that to you to do on your own, because there's about 3 different ways of doing this. And if you need help with it, you could send me an email and I could send you in the right direction. But you do want to the chances of them asking this again now, it's 2025. So the chances of them asking in 2026, you probably take it 2027 is what I'm thinking. They might come up again. They do have a tendency to repeat questions, by the way. So what is meant by a safe state? Well, that's a generic question. And to answer that question for you, because that's the topic we're talking about right now, is if all processes P0 through 4 can get their allocations and they can all be serviced, then it's a safe state. If one of them is left empty-handed, can't get the resource, then it's not safe. That seems like an easy question for them to ask. And then this is the matrix approach to it. So, is the system in a safe state? If yes, show the safe state process sequence, which basically you're going to be explaining which order you're going to run these in order to create that safe state. Because running them like this is 99.9% of the time not feasible, not going to work. So it's the order that you're doing it in. But here we go. Look at that, producer consumer. So consider the following pseudocode for producer consumer problem using semaphores, mutex. We have a mutex 1, empty and full. And so you're looking at the code here, then you're going to ask questions about it. Explain how mutual exclusion is enforced in the solution. So I can tell you how the mutual exclusion is enforced. We're waiting. Producer's waiting on consumer and consumer's waiting on producer, which, if you think about the order, wait empty, wait full, wait mutex, signal back and forth, signal back and forth, signal mutex, signal full. So they're both oh, that's weird. They're both waiting. I'm trying to get out of that. Okay. Didn't mean to click on that. They're both waiting for each other to signal. So some follow-up questions on that one. Could deadlock occur? What would happen if the order of the wait operations in the producer were reversed? Yeah. So that's stuff that you want to be familiar with. So this stuff is relative. So anyway, let me get out of here because I cancel. How could you save something that was online? I guess you can save it. Huh? I didn't know you can edit a PDF online. Anyway, I just wanted to show that to you because if, when I was a student, I want to know what tests I'm going to take in the future. I want to know where the sample problems are. So anyway, so yeah, we're looking at the safe versus the unsafe. If we take a look at the Java examples for this, we already did this one. We're looking at the banker's algorithm here in Java. And again, just like the other one, it has it all in one file. So we have a banker and we have 5 processes and we have 3 resources. So that's the other thing too. You need an uneven amount of resources. If you have enough resources to service 5 processes, you don't need an algorithm for anything. But in here, we have 5 processes that need that are going to share these 3 resources. And so we're going to calculate the need. So your methods, the way that you're going to implement this, you're going to run calculate need, which basically is you're going to figure out from the allocation, the starting allocation. And it's mimicking what you're doing in that matrix if you solve it mathematically or logically. Calculate what you need, find out, and it's not a matter of just adding up what everybody needs. It's the order. So you're gonna make sure that the is safe comes back true for particular orders. So, and it's basically just using the word safe to kind of indicate it's a good selection. So we have a loop with an inner loop, and we're going to have a need for each instance is the maximum instance minus the allocated instance. So what have they got allocated and what do they need? That's what they have left over. We're going to keep track of it in a array, double array. So each process is going to have a separate need associated with it. And then we have an is safe, where we're going to take a look to see if we have after we've calculated the need, we're going to set a Boolean flag to, are we finished? Are we not finished? And then we're going to go through sequentially through the list to see if the combinations, which is the order that we're doing something, is safe, which is basically very similar to how we would do a resource graph if we were doing that, where we would have different orders put together, and they call it a schedule. And then you can have a score for each one of the schedules. And then you pick which one has the best score, depending upon the criteria. So, which means, you know, maybe it has the most allocated resources for each process, for each request. Basically, we want to fulfill all of the requests. And in order to do that, we have to do it in a particular order that makes it safe. All right, which is basically the banker's algorithm in a nutshell. So this one is good for allocating a limited number of resources to a lot of different processes. So, all right, so we have while count, we've got some things in here, some flags set to see if it's found or not found, safe or not safe. The system is not in a safe state. It will be returned if the need can't be met with the current allocation in the order that it was requested. So we have a main method here, and then you'll see the matrix going on here. And if you read that section, you'll probably understand a little bit more about it. But we've got the available instances of the resources. We've got the maximum resources that are allocated to each one of the processes. We've got the resources that are allocated, the ones that are currently allocated. And then we're just going to do a check, follow to that method to see if it's safe. So let me fly through. I went through the other ones too slowly. So read, write. Oh, we're done with that one. Okay. So the readers and the writers. So we're done with that one. Done with that one. Readers and the writers. It's like the mamas and the papas, readers and the writers. That was an old rock group. Okay. Guys are not in humor mode today. All right, so we got P thread going on here. Readers, writers. So in this particular scenario, it's the database scenario. So we have any number of readers can happen anytime simultaneously. So we have a split, kind of like a split personality here. But when a writer comes into the system, then we have problems, because the writer is going to change the data. It's going to make it inconsistent. So the readers are reading an old value, or better yet, the readers are going to do a write on an old value as well. So the writers need to be synced as well. So we need a mutex to keep track of the writers and an accounting semaphore to keep track of the readers. So we can do them independently. If we used a mutex for all of it, it would be a very slow database system. So databases get around it by using a commit and a rollback and a what they call it a synchronized schedule. So at the end of the day, all of the readers all of the writers who have made updates to the database table will go in the order that the writer was allowed to access it. So at the end, this needs, in this particular scenario, you need to reconcile it at the end. Because you can switch the order around and you're going to get a different answer. So if I like deposit, let's say this is a banking scenario and I deposited $10, but then I withdrew $20, but I had $10 in there. If I did with the withdrawal before the deposit, then I'm going to end up with a negative $10, even though I had $20 in there because of the read write syncing. So you have to pay attention to the order that things are happening in. So we're gonna do P threads here, and we're gonna create a mutex, and then we have the writer, we have the reader. Two threads that are going to be racing to each other to use. And in the scenario for main, we're going to create 10 readers and 5 writers. And we're going to control them with a mutex. And this is the C version of it. We are going to have just use for numbering the producer and consumer. Well, this is not a producer consumer. I should take that out. I think I modified this example for producer consumer, by the way. It's very similar. Reader writer. So we have a reader threads, writer threads. We're going to set them running. And then we're going to use the rules on the readers and the writers, whether or not they're actually able to obtain the lock or not. If they're obtaining the lock, then they can write if it's a writer. So it's all about enforcing the rules on when a writer can write and when a reader can read. So, all right, kind of flying through this now because I'm running out of time, but the Java implementation. Semaphores. We've got a class read writers problem. Yeah, it's the main program here. So even though we're using semaphores, we're really using a mutex here. So because we have semaphore 1, we have 2 of them. We have a read lock and we have a write lock. You do want to keep 2 separate locks because you do have 2 separate activities. So one can be a semaphore, the other one can be a mutex. We've got 4 minutes left. Here we have the read that's going to implement runnable. And we're going to implement the run method. And then read lock.acquire, read count plus plus. If the read count is equal to 1, then write lock.acquire. So we can run the lock. And then the read.release. So we're still using the acquire and the release. And we're testing to see, in this particular case, the system.out.println, is it reading? Has it finished reading? We're going to sleep the threads in between. So the read lock.acquire, we're going to keep a counter of how many readers there are. Because if there's more than, it doesn't really matter for the readers. There can be more than 1 reader, but we don't want more than 1 writer. So we want 1 writer at a time with multiple readers. But then once a write has occurred, we need to make sure that the readers refresh. So the readers get knocked out and then the readers come back in. So, all right. I got 3 minutes left here, so let me, oh, that was the last one. Sleeping Barber is actually the last one. Yeah, don't think you actually have to do the Sleeping Barber for any of your homework assignments for this class, but it's not a bad IPC algorithm to be familiar with. It has shown up on the capstone occasionally. With this one, you've got, and I'll just give you the scenario as a recap, and you can follow along with the code. I don't have the C version of it, I don't think. I just have the Java version. I do. But in this particular scenario, you've got one resource that is being requested by many other threads. So you got, and the threads are the people who want a haircut, just like this scenario. You got 20 people come into a barber shop and you got 1 barber. And so in order to fairly service all of those threads, in this particular scenario, you queue them up. So you put them in a queue and then you go through each one of them. And the queue is generally, you know, first in, first out kind of thing, like a regular queue. And you can keep track of each one of these customers by their order in the queue. And then if the queue is full, which means the number of chairs in the barbershop is full, then you can stop letting threads come in. Basically just deny the resource. And so you can decide how many customers you are going to allow in there. So it's pretty customizable, and it's basically, you know, relying upon queuing. I don't know if this one has ever been tested, actually. It's not a bad one, though, to be familiar with just in case.